Let me start this talk with people. At Stanford, we have recently established an Institute for Human-Centered Artificial Intelligence. The three themes of the Institute link between people and AI. We believe that for developing the next generation of breakthroughs in artificial intelligence, that firstly, AI must incorporate more of the versatility, nuance, and depth of the human intellect. However, as AI is widely deployed in the real world, we are no longer just technologists in a lab, and the development of AI should be guided by a concern for its impact on human society. Finally, we emphasize AI as the next generation in the development of human tools, and argue that AI should augment human skills, not replace them. Overall, we think it is very important to build AI that supports us in our human goals, but is constrained by our human values. Back to people. People have needs for information, communication, business needs, and social needs, such as to feel that other people get them. They achieve these goals using the most marvelous of human inventions, language. For computers to communicate with us easily, to receive and give appropriate information, and for humans and computers to feel that they understand each other, computers need the ability to understand human languages. Most people primarily use their computers to communicate via human language. Half of the world's population uses both one of the big four social networking apps and one of the big four messaging apps each month. Spoken language interaction is taking off with modern virtual assistants. There are more than 100 million Alexa-enabled devices in use today. Google Assistant is available on over 1 billion devices. The rate of adoption for smart speakers is faster than it was for cell phones. Spoken language is also key to enabling productivity on mobile phones. On these devices, reading is difficult, and input on virtual keyboards is tedious. They're even harder to use for people doing a physical task, including driving, elderly people, people who use Chinese characters, and the many people with low levels of literacy. Notwithstanding the awesome texting abilities of teenagers and those in their 20s, spoken interaction with phones is much more efficient. My Stanford colleagues Sherry Wan, James Landay, and Andrew Ng found that speech recognition is now 3 times as fast as texting for such users, even after factoring in the time to correct speech recognition or texting errors. However, while computer speech recognition is now excellent, the understanding of human language utterances lags far behind. And that is the main topic of my research. Sometimes when I ask Siri, what was the final score in the Women's World Cup today, it works beautifully and gives me the answer. But most often when I ask my digital assistant for an answer, I get something like this. How do I see my subscriptions on the iTunes store? I found this on the web for how do I see my subscriptions on the iTunes store. What that means is notice again that the speech recognition was perfect, but the phone is basically confessing that it had no idea at all what I meant. So despite the fact that the answer exists on the support website, it's not able to understand my question well enough to be able to give the answer. And so a lot of the research I do is how to get better natural language understanding to try and push the field forward to allow this kind of language understanding by computers. For any of commands, questions, or human knowledge, most of it is in the form of human language material, either speech or text, and we need computer systems that can efficiently understand human languages. Fortunately, there have been enormous improvements in natural language understanding in the last 2 years, driven by the development of a new generation of deep contextual representations. In particular, the BERT model has become very famous as a large language model, though there are now generations of other bigger, more recent ones, including ERNIE, GPT-3, T5, Roberta. These models introduce a new neural architecture. So apart from the left column, all of these models are transformer models. I'm not going to have time today to explain all the details of how transformer models work, but the starting point is that their task is to predict words that have been masked out in a piece of text. So we have Judiciary Committee mask report, and the model wants to guess what word was masked out. And the style of the model is that it is then working out attention scores between each position and every other word to compute information about a contextual word representation. So for each word, it calculates a query vector, which is then compared to key vectors in each position. And then based on those weighted attention scores, you're then combining together a weighted value from each word to come up with a new representation for the word committee. And then these are deep networks with many layers, which repeat this process over and over again. So you get a strongly contextualized representation of the meaning of words and then progressively the meaning of larger linguistic units. These models have been super successful. So basically, for any natural language processing task, the state of the art in 2020 is the performance you can get with these large contextual language models. I'll just mention one example here. So the Allen Institute for Artificial Intelligence has worked for many years, well over a decade, on the task of learning scientific knowledge and being able to answer science questions. That's its Aristo project. And in its origins, this was meant to be the task which would lead to the renaissance of research and knowledge representation and reasoning. But what they've found over time is exactly the opposite, as shown in this paper from last year. So for these science question answers, you can get a certain distance with just information retrieval. The knowledge representation reasoning systems can do a bit better than information retrieval, but unfortunately actually often not much better than information retrieval. But as soon as you turn to BERT-style models, you're getting an enormous performance increase. And going from BERT to a later generation like Roberta, you get even more increase. So these Aristo BERT models are just like the regular BERT models, apart from they're trained on a lot of scientific literature rather than general English. And the eventual Aristo system is an ensemble, but as you can see, it's really not much better than the performance of Aristo Roberta. I want to give you more sense of what's powering these results, and then to talk about some work that we've done to try and improve the usability of these models. So I'll show you quite a few results on the GLUE benchmark. And so this was a benchmark of tasks testing natural language understanding. Some of them, whether you can make inferences about text, such as the example here, where Jainism hates nature is contradictory to the fact that hills and mountains are sanctified, or other ones can be things like pronoun interpretation, deciding she is nosy, the she refers to Susan, not Anne in the lower example. For these GLUE benchmark tasks, in the last couple of years, enormous progress has been made. So compared to the models of about 2016, such as based on gloved word vectors, that we've seen the error of these models reduced 3 times. And with successive generations of large contextual language models, performance is getting better and better. Indeed, the performance of the latest models like Albert and Roberta is actually better than the performance that's been measured for individual humans doing the same tasks. However, if we decide to change the x-axis to now look at the amount of compute required to get these results, you start to see a rather different story. So early models like the glove-based and Elmo models used virtually no compute, you'd say, in retrospect. And as soon as one started into the BERT models, either the small BERT model or the large BERT model, you're starting to use massively more compute. So the BERT-based model is using 64 exaflops, 6.4 times 10 to the 19 flops to train. The BERT large model is using 190 exaflops to be trained. So BERT large uses 60 times more compute than Elmo in its training. But that was only the start of things. As we proceed on from there, it's only increased by further orders of magnitude. So the Roberta model uses 16 times as much compute as BERT large, 3 zetaflops. And then even more recent models like Albert and T5 use about 10 times as much compute as Roberta, about 30 zetaflops. And GPT-3 is up there in that range as well. So my colleague Andrew Ng likes to say AI is the new electricity, but what instead we seem to be seeing here is almost the opposite. It seems that electricity is the new AI, that we're getting better results simply by using more and more compute to train our models. So we've been interested in particular my student Kevin Clark, on can we get the good effects of mass language models with less computational resources? Well, one of the ways in which these models seem efficient is that although they do the computation for all words, they really only learn on the masked words. And another way that they're perhaps inefficient is the big softmaxes to predict individual words. So we explored a different pre-training task where we noise the input by replacing some of the words with similar words, and then the model is simply asked to predict which words are original words and which words are among the minority of replaced words. And for both of the reasons given, this is a much more energy efficient way of doing pre-training of large language models. And so we can use a fraction of the compute and produce models that work as well. So if we look at largish models of a large size architecture, we can build something that requires the amount of training of a BERT large, but works considerably better on question answering than models that take 5 times as much training. And if we head into the small, we can start building smaller and smaller Electra models. So we can build a 6.25% Electra model, which can be trained in hundreds of times more quickly than a BERT-based model. And its performance isn't perfect, but its performance is still pretty good, better than an Elmo's model by several percent. And it's then of the kind of small size that any graduate student can train. It only takes 6 hours to train on a single GPU. Let me now turn back to conversational AI systems. A very real possibility is that virtual assistants will replace the current phone or computer screen-based internet. Assistants will be able to execute tasks for us on many devices, often in a hands and vision-free way. Traditionally, speech dialogue systems have been mainly handcrafted rule-based systems. They use a little machine learning for intent recognition, but then they're largely followed by templated generation. Can we now use deep learning to build such systems? This is a project that a number of us at Stanford are interested in under the Open Virtual Assistant Lab that's led by Monica Lamb. I'm going to mention a couple of pieces of work, one on training task-based dialogue by Giovanni Campagna, and then looking at aspects of our conversational social bot. So for task-based dialogue, we'd like to have flexible natural language programming so that we can go from human language intents to a formal programming language representation that we call the Virtual Assistant Programming Language, or VAPL. And the secret is we'd like to be able to build these systems that work for all sorts of niche tasks, so that every time someone has a new Internet of Things device, a new light or alarm or toaster, and every time someone sticks up a new web API, it's not that we have to then say, oh, we have to build a training set of 50,000 natural language utterances. We can very quickly get a natural language interface working with that system. And the question is, how can we do that? And so that involves building a neural semantic parser that can translate from natural language to instructions in the VAPL code that will execute the correct command. And this work is looking at coming up with a method, Genie, which lets us successfully build neural semantic parsers without requiring a huge amount of hand-labeled training data. Traditionally, semantic parsing has been hard because it only works well if you have lots of annotated data with which to train the neural network. And that's very expensive and impractical for this new world. So the idea of Genie is to be able to generate good quality annotated training data at scale relatively cheaply. How do we go about this? Well, the starting point is that Genie has an API library. So these are the different commands that it can actually execute inside the VAPL programming language. And for each of these commands, there'll be a basic natural language realization of it. My Dropbox files in X or post X on Facebook. But the advantage of having a formally specified programming language is then we have compositionality through the programming language, which can then also lead to compositionality of the natural language. So when we combine things like, when there is a cat picture, post it on Facebook. We can compose together the basic API calls with VAPL language constructs and produce at least an awkward natural language form for it. We then want to be able to get beyond that. So we start off with synthesizing a large number of expressions, just using the data that there is, but that won't show us the whole range of natural language. So we do a couple of things. One is we do actually collect some human data. We ask humans to paraphrase some of this data that we have synthesized, because that does unlock parts of human language capabilities that we can't discover by just composing in a rule-based way commands. The second thing we can do is greatly expand the data by augmenting it with entities and paraphrases, so automatically changing things using other person names or other phrases we know to be similar. So using this idea, we can produce a huge data set of 3.6 million augmented training items, despite only getting a very small number, about 24,000 human-given paraphrases, so only costing about $8,000 on one of the Turka platforms. We then use this data in a neural model where we're using a modified Decker NLP model, the model developed by Brian McCann and colleagues at Salesforce for semantic parsing. And this shows you some idea of how it works. So we compare in the light blue the baseline model that's just trained on supervised data versus the effectiveness of the Genie model. And what we find is that the baseline model just doesn't generalize very well, and its performance on the test data is quite poor. Where the Genie model is general, its performance is much better, and its generalization capability is much better. And this is testing on real user data collected from if this, then that. And I mean, actually, the only previous work using this data set as a test set got almost no performance. It only got 3% performance. But human language isn't only about giving tasks and commands. A lot of human language is about chatting. And we've also been working with some of my students, Ashwin Paranjape and Abigail C., on building a conversational social bot. Most social bots aren't very good at the moment. They have too little user initiative, forcing people into rigid dialogue trees. They can only chat about a narrow range of topics. They don't support niche interests. They provide information, but not in a conversationally natural way, and they don't show interest or empathy for users' experiences and emotions. And so the result is you have unengaged users. So what we'd like to do is instead have a social bot which allows the user to drive the conversation. It chats about any topic, provides information conversationally, and engages empathetically with users' everyday experiences and emotions, resulting in engaged users. And so the mechanism that we've been exploring to do that is making use of a neural generator to produce natural chat about a user's personal experiences and emotions. So the bot does start off with a handwritten starter question, but after the user responds, we're then generating responses using a neural language model, a GPT-2 model that's been fine-tuned on empathetic dialogue conversations. And that allows us to quite naturally follow along a conversation with the user for several turns. Eventually, these models do tend to degrade, and so part of what we then do is cut things off and return to sort of a hand-guided new direction to take the conversation. We wanted to do a bit more to encourage sharing and emotional conversations. Neural models work better when users give longer, more contentful utterances. So we tried some conditions to encourage that. We tried talking about the bot's own feelings before asking a question, sharing personal anecdotes, and these are indeed effective methods to get the user to give longer responses. And so the result is that we have a model that can chat about any topic. So the average user talks about 8 different entities on the conversation, and about a third of the conversations have at least one rare entity, these ones over on the left side of this graph. And indeed, people are happier with their conversation if they've gotten to chat about some rare entity. Okay, there's just one more example of natural language use that I want to touch on before concluding. This example is a little bit different. It's showing how natural language can be useful in medical applications. A lot of the application of AI to medicine has concentrated on doing visual tasks of doing various kinds of processing of images. And that's a great goal. But the problem is annotations are very scarce, and it's hard to build up large data sets of getting doctors to provide training data for images. So typically, the two main methods are to use just a little labeled data and transfer from general data sources like ImageNet, but that suffers from drastically different image characteristics, or to look at the textual reports that doctors do write anyway, and to do rule-based extraction of labels, enabling supervised learning. But that's inaccurate and hard to generalize and scale. So what we've been exploring is whether you can do much better with unsupervised learning. And people have tried this for image-only unsupervised learning using methods like SimClear and MoCo. But because the images tend to be highly similar, that tends to be an ineffective objective. So our idea is, well, doctors write narrative reports on what they find anyway. So can we just use these natural language reports as effective additional material to drive unsupervised learning about images? And so that's what our model, CONVERT, Contrastive Visual Representation Learning from Text, does. The core idea is that we're combining images with true and wrong natural language reports about them, and then we're doing contrastive learning to maximize agreement on the true versus the false image-text pairs. So we pre-train on 2 medical data sets, and we evaluate their performance on 4 medical image classification tasks. And what we find is that using this much superior form of pre-training, we can then work with much less hand-labeled data, about 10% of the amount of hand-labeled training data of other methods, and outperform other methods on this task. In particular, if you compare the unsupervised pre-training with language versus vision-only unsupervised pre-training, the middle 2 bars in each diagram, pre-training that involves language is much more effective. Okay, let me just now close with a final thought on the role of human language and artificial intelligence. When thinking about artificial intelligence, people normally fixate on modeling an individual human brain. But human language is powerful precisely because it gives groups of people a way to network human brains together. In fact, an individual human may not be much more intelligent than a chimpanzee or a bonobo. These monkeys have been shown to also possess many of the hallmark skills of human intelligence, such as using tools and planning, and they have better short-term memories than we do. Within the history of life on Earth, human beings developed language really recently, but the power of communication set off our ascendancy over other creatures, even though we aren't as strong as an elephant or as fast as a cheetah. It was much more recently again that humans developed writing, that was about 5,000 years ago, allowing knowledge to be communicated across distances of time and space. In just a few thousand years, this information sharing mechanism took us from the Bronze Age to the smartphones of today. The power of language is truly fundamental to human societal intelligence, and hence to the future of a world with artificial intelligence.